Hello. So the experiment that we did today that we're going to be trying to explain with this picture up here was we experimented with supercapacitors, which, in simply put, we took some carbon and attached it up to a bit of energy and tried to make it work and store energy and output. So I'll let you all see this while the picture is explained.
Okay, so as you can see in the first panel, it's a marathon, and you can see that there's a little kid at the end, and then somebody who is very familiar with running marathons in the middle, and then a lady at the very front. And the guy in the middle represents the supercapacitor, and the kid represents the battery, and the lady at the front represents a capacitor. And then in the second panel, you can see that the lady is starting to fall behind, and the guy has now taken over the lead. And then at the end, you can see that the little kid has short strides and ended last. The lady had average strides and ended in the middle. And the guy had long strides and ended first.
Cool. I'm going to take this off. It's going to be a little loud. So I'll give you a little bit of a brief background with power and how this relates to batteries and how this all relates to the picture up here. So power, simply put, is energy expended, and energy is how much stuff or how much potential is stored. So when you're putting this in terms of batteries or in capacitors, a battery basically stores energy, so does a capacitor, and then releases it somewhere else. This is what you do with your phone, with your car. You charge something up and then have the energy expended sometime later. So with a battery, as the group earlier was explaining, it has high energy but low power, which means that it can store a lot of stuff, but it can't really release it quickly, which a capacitor can do. Now, a capacitor has low energy but high power. And kind of in the middle of this, when you increase area and decrease the distance between plates, which we did a lot this morning with nanotechnology and getting stuff small, you get a supercapacitor, which has high-ish energy and high-ish power. Now, this kind of relates to all this picture you're seeing up here by the first runner going off to the very fast head start, the girl up there. We thought this represented the capacitor, where she got off to a very fast start. Now, as we keep going along, she kind of starts to fall behind. That's because she has she has high power but low energy, which means that her stamina isn't the best. Now we can see the person who actually wins the race in the very last one, that's going to be our supercapacitor, which means that he got off to a slower start, but because he had a lot of energy and a lot of power, he could stay moving for a very long time. Now, at the very end there, who's lagging behind the entire time, that's her battery, unfortunately. And so we also kind of analyzed the quotes and the strides at the bottom, which you can probably see better than I can. So with the quotes, the supercapacitor has run 20 marathons before, and that's kind of representing how durable supercapacitors are. They can go for, I think the statistic was 5 or 50,000 times, while a battery can only run like 5,000 times. So it's much, much more durable. Also, with the capacitor saying that she cannot keep up, that's because she has that lower energy and she doesn't have the power or the energy to keep up. And then at the very last part, the supercapacitor is saying that he's pacing himself, and that's because he has a lot of power and a lot of energy. So yeah, and thus, I'll give you a little bit of a pun, the supercapacitor wins the race in the long run.
So overall, we thought the analogy was very creative and straightforward, and we thought the different speeds are very obviously representing the supercapacitor, the battery, and the capacitor, and the strides also really let you know that. And the distance of the race basically was also a very good way to explain the distance that electrons need to travel. But some limits on the analogy that we saw was we couldn't really see that it captured the relationship between the area of capacitors and the distance electrons need to travel, because as area increases and distance decreases, efficiency increases, and that's not really shown here. And we also didn't really see how power versus energy was demonstrated, because batteries basically have energy and supercapacitors have power. And we figured that people could basically be like running different races. So the battery could be running a longer race but running slower, and the capacitors could be running shorter races faster. yeah, that's really all we thought. Cool. Thank you for listening.
Thank you.
Okay, questions?
What do the times represent, the actual times that it took them to run?
So I think the times were their attempt at demonstrating the power versus energy, and also just how supercapacitors are more efficient than capacitors and batteries. But I think that it was kind of missing that, like, batteries, while they are slower, they can also keep going for a longer time.
So, okay, so the times I think are like 5 hours, 3 hours, and 2 hours, which are like sort of real marathon times. So now if you wanted to make them like real battery and supercapacitor times, what would you change them to?
Oh, do you want me to answer?
Whoever.
Sure. So supercapacitors probably cannot run for 2 hours. That's a very long time. This is a marathon given, and this is trying to represent that they're better in the long run again. But realistically, they would have to recharge over and over and over again, but they can recharge very quickly in order to get there. So
just like order of magnitude, what kind of times? These are sort of long, medium, and short marathon times. If they wanted to be long, medium, and short energy storage times, like what times would you use for each person, vaguely, or just like order of magnitude?
Sure. In order of energy storage, the battery would definitely last the longest, as they have high energy and low power. Supercapacitors would go next. They have high-ish of both power and energy, and then the capacitors would go last, having very little energy but high power. That's why they run so fast but can't get very far.
But can you, one of you, the others of you guys, can you actually guess at times, not order of times, but actual times?
I mean, today in the experiment that we did, we lit up LED lights with our supercapacitors, and I mean, those only went, they would only be running for about a couple seconds, and then they'd have to recharge for like 30 seconds, and then again, they'd just be, the lights would run.
So supercapacitors order a few seconds. Everybody has a battery. What's the sort of time scale for batteries?
A few hours.
Hours. Okay, so we've got hours, seconds for the regular capacitor. Any idea?
I mean,
Probably seconds or milliseconds.
Probably microseconds.
Microseconds.
So that was a great question, because like the Army one, there's only a finite scale that the real systems can have, but the science systems can be orders of magnitude different in scale. Okay, other questions? Actually, there's a parent. Parents get first priority.
So in both cases, I think the cartoon has done a good job of conceptually demonstrating the difference between batteries, capacitors, and supercapacitors. But could you explain a little more what the actual lab was like this morning, where you were exploring? You mentioned it a little bit. Could you explain what you did this morning?
So basically, we used a bread box?
Yeah.
Something called a bread box, and we basically put like wires, and we wired our own capacitors, and then after that we wired our own supercapacitors, and we basically just made an LED light, work by charging the capacitor and then running it, and we ran like parallel circuits after that we had two capacitors together, and we ran parallel circuits to see that the light would run longer because there was more power.
So you actually made your supercapacitors. How did you make them?
I cannot remember the exact chemicals that we used.
Doesn't matter the exact.
Citric acid.
Just
Okay.
just a big idea.
Basically, we had carbon, which in our form, I don't know if we actually had graphene, but we had some kind of carbon base that could store energy, and then we had.
What was special about the carbon?
Play-Doh.
It was Play-Doh we like.
Well, you made it Play-Doh like, but what was its what made it useful? Was it a big chunk of carbon?
It's a conductor.
Was it just a big solid piece of carbon?
It was powder. Yeah. Or like powder that we made into like small bits.
The audience
Small
seems to know the
bits.
answer.
I told at the very first day. I told you what was the answer. The answer to every question.
High
gonna be
surface area.
It was very high surface area carbon. Told you it was going to be the answer to every question.
True. So with our high surface area carbon, we were able to store a lot of energy. I believe this calculations came down to our little chunk, like 2 grams of carbon, could store 500 meters squared of just surface area, which, if you think about it, like something in that big of an area can store something half the size of a football field. Was it?
So
2 football fields.
That's how much surface area it had.
Yeah.
Then what did you store?
Oh, we stored electrons on
Stored
it.
electrons, and where did they sit? Why are electrons and numbers of football fields relevant to each other? Where did you put the electrons?
I'm kind of confused about that question.
It was on the carbon. I mean, yeah.
On the surface.
And so-
Surface of the carbon.
And so since there was high surface area on the carbon, we could fit a lot of electrons onto it and therefore conduct finish the circuit.
Good job. Okay, I have one more question. So there's a lot of dissing of batteries here, but in fact, batteries are everywhere and ubiquitous, and we're not throwing them all away for supercapacitors. So that means batteries actually do better in a whole lot of cases. So what race would the battery win?
Probably a marathon, actually.
Well, okay, but so this was okay. I don't know what race this is. So given that this was drawn as a marathon and the battery didn't win, what race would the battery win?
Any long distance race, because they can last a lot longer, and they store more energy. I don't know if that's what you're looking for, but longer.
Much longer race.
Yeah.
They totally. We use batteries for everything because they store way more. They're just slower. But so a longer race, both of those guys would have been like just lying down on the edge of the road, and the battery would still be running. Yep.
When you first talked about supercapacitors, you said that they were better than capacitors for 2 reasons. First, you increased the surface area, and then the second thing you mentioned was that you decreased the distance. How did you use your chunk of carbon to decrease distance as well, or did you not take that into consideration?
So they're not necessarily better than capacitors. They both have their merits.
No, this is a different question.
Oh
Yeah.
yeah.
So
Yes,
okay.
yeah.
Okay.
Just answering the first part. Yeah. So basically, we use the carbon to actually.
Sure, I can take it. So in normal capacitors, it's usually steel plates. And steel plates are kind of chunky. They are very big, very hard to work with if you're trying to make a small scale thing. The nice thing about carbon is that when it forms up with whatever chemicals we used, they could make very structures that had very small spaces in between what you call plates, or parts that you can have electrons jump between, I guess, and are being stored on. And so in order for this supercapacitor to be made super, we had a bunch of those little plates in a very small area.
So that was basically right, but I want to just get the true essence. So in a parallel plate capacitor, you have 2 plates, and the distance is just the distance between them.
Yes.
What's the relevant distance here? It's the distance between what? The surface of your carbon and what? What's sort of the other plate? And it's not actually a plate.
It's the electrons, right?
The electrons are on the surface, so that has one charge. What's the thing that has the other charge?
The electrolyte solution?
Yeah, it's actually ions in solution, and that's what makes the distance so small, because it's not actually 2 plates, it's 1 plate, and then the ions in solution. That was good. Okay, I know there were some other questions, but we will never get out of here if we do not move on to the last topic. And so who was the author was another group here? Can they stand up? Are they? Yeah, good job.